Welcome viewers to today's Stop Lab. And have you ever played with a spring? You stretch and compress it back to the original length. Well, in the spring, there is a specific physics theory in it, and that is the Hooke's law. Well, in today's experiment, we will use actual equipment to prove this theory.
There are many applications of Hooke's law in life, such as the spring matrices and the spring suspension systems. The spring matrices can be compressed according to the weight of the person. The same goes for the spring suspension systems. Both of them can make the person feel more comfortable.
Okay, now let's just go further and discuss Hooke's law. Now it mentions there is a spring and it has the original length of L. We apply the force on it, it will extend it. And this extra length is what we call the extension, X. Now, what is Hooke's law? It's basically that the applied force equals to K, the spring constant, times the X extension. So X has a unit of meter since it's length, and any force is Newton, so we can get that the spring constant K has a unit of Newton per meter. And in today's experiment, we're gonna figure out the K of our spring. And okay, so now let's welcome my partner Steven to tell his part.
Alright, and here is the main character of this experiment is a spring, and we will hang it on this super straight stick. And then we will use the meter rule to measure the actual extension to the spring. And here is a very interesting stuff. It's a device called the force sensor. It will record the actual force exerted on this spring. And with these two figures, we will now actually can figure out or measure the K constant. Well, it's quite obvious, and let's do the experiment.
So now let's get started the experiment. For the experiment, we have the tension sensor, and by pulling the spring, in order to eliminate the mistakes, I'll try my best to pull the integral force on the spring.
And I will use the meter rule to measure the actual extension as accurately as possible.
Now we got different kinds of applied force. It's 2 Newton, 3 Newton extra, and responded extension. So now we got all factors we need to calculate the spring constant. So now we can actually draw a graph of force against the extension, since K is exactly the force over extension. So when we draw a graph like that, the gradient is exactly the spring constant.
And the spring constant is almost like 0.22. Yeah, almost.
Okay, now we can make a graph based on our data. So basically the x-axis of the graph is the x extension, and the y-axis of this graph, which is the dependent variable, is force applied. Now here is a straight line. You might be questioned that why this line didn't pass the original point, since we didn't type in the 0.0 point, but that's not important. As you can see, most point is perfectly fitted on this line, and the gradient of this line, which is the spring constant, we can see clearly is around 0.22.
The errors in this experiment may be the measurement errors, including the stadium difference, and the application of the force may not be in the exact integers. But in fact, we really tried our best, and I think we all did the best we could.
Okay, viewers, that's all about this experiment, and it's time to end.
Remember to follow us.
See you next time!